Jai Hind to all of you. I am Dr. Ritish Kumar. I am going to present the topic noise in PCN system. Actually, I am assistant professor in Department of Electronics Communication Engineering, Ajay Kumar Engineering College, Ghaziabad. So today we will discuss the topic of noise in PCM system. PCM is nothing but pulse code modulation system. So here we analyze the noise over the PCM system. So this is the university syllabus. University syllabus divided in 5 units, where the topic of pulse code modulation lies in unit number 4. As you can see, pulse code modulation. Right. So here we analysis the noise consideration in PCM system. Right. So first unit is related to the AM, second FM, and the third unit is the random variable, and fourth unit is related to the pulse modulation, and fifth unit is related to the digital modulation technique. So here we'll discuss the PCM system. These are the books, recommended books. So I will prefer these two books. First one is Simon Hagen, and third Tobin Schilling, Principle of Communication System. So let's begin the topic, noise in PCM system. Right. So I hope you all are aware about the pulse code modulation. In the pulse code modulation, there is a process. First, you have to do the sampling, then quantization, and then encoding before the transmitting the information. Right. So during the quantization, you will get the quantization error, and this error also known as quantization noise. Right. So in PCM system, there are two kinds of noise you will get. The first one is the channel noise, and second one is the quantization noise. So channel noise can be eliminated with the help of regenerative repeaters, which you can apply during the transmission of the information. It can be removed or eliminated by regenerative repeater. Regenerative repeater. You can also call it RR. So channel noise can be eliminated or removed, while the quantization noise cannot be. So there is a significant effect over the information in the PCM system. So we need to analyze the quantization noise, right? So quantization noise. So quantization noise we can represent with the help of QE. By QE, as we know, plus minus delta by 2, right? So delta is the step size. So if you want to reduce the quantization error, you have to reduce the delta size, that is step size, right? So as we know that delta is equal to B max minus B min divided by L. L is the number of labels, and L is equal to, we can write 2 to the power n, where n is the number of bits per sample. So in other words, we can say, if you want to decrease the delta size, you have to decrease the dynamic range, or you can increase the value of n, for which you have to increase the number of bits per sample, right? So there is a relation between, to reduce the quantization error, you have to decrease the step size, and for decreasing the step size, you have to increase the number of bits per sample. This is the main motto to reduce the quantization error. Now, what should be the analysis of quantization error? So, for which we have to take the signal to know the what is the effect over the noise over the signal. We need to calculate, we need to analysis the signal to noise ratio, signal to noise ratio. This is nothing but it is the ratio of signal power to the noise power. To improve the signal to noise ratio should be as high as possible, because you have signal power should be as high as possible or noise power should be as low as possible. If you combine these two statement, you need to have the signal SNR as high as possible, right? To have the efficient communication, signal to noise ratio should be as high as possible. So, in the case of quantization error, I will call the SNR is signal to quantization, SQNR, signal to quantization noise ratio. I can write this S upon NQ, where NQ is the quantization noise power. Right. So, this is the main overview of the signal to quantization noise power. So, to have the efficient communication, this signal to quantization noise ratio should be as high as possible. Now, let us begin how to calculate the signal to quantization noise SQNR in PCM. PCM is pulse code modulation, right? So, how we can calculate the noise power? So, noise power here quantization error we can represent with the help of QE. Quantization error is represented by QE, right? So, if you have the power spectral density of the QE, then you will get the quantization noise power by taking the mean square value of the power spectral density of quantization error. So, NQ, as we can say, quantization noise power is equal to mean square value of QE. If you have the power spectral density of QE, then you can calculate the mean noise power. This is noise power. This is mean square value. So, here I am assuming that the quantization noise error, the PDF of the quantization noise error is uniformly distributed, just like in this way. This is a PDF of noise error. As we know that the noise error can be lie in between plus minus delta y2. So, this value is plus delta y2 and this value is minus delta y2. As we know that the properties of PDF is the area under the PDF always be equal to the unity. So what should be the value of this to have the unity area? This value should be this total span is equal to delta, then this value is equal to 1 by delta, right? So assume this is a uniformly distributed uniform distribution, right? So with the help of this PDF we can get the noise power by taking the mean square value of the given PDF, right? So you can write the mean square value minus general formula minus infinity to infinity. Here the random variable you are considering is QE. So as we know x square fx dx, so here x is replaced by QE square, right? F Q QE and dQE, right? So this is the formula for mean square value for quantization error. Now this the value of FQE you can write from the this PDF. So and it lies in between minus delta by 2 plus delta by 2. So this minus infinity to infinity is replaced by minus delta by 2 plus delta by 2. Sorry. Okay. Just a minute. So this should be minus delta by 2 plus delta by 2 QE square, and the value of FQE is 1 by delta dQE. Now you have to integrate the QE square with respect to QE. So this you will get QE 3 by 3 minus delta by 2 to delta by 2. So this should be 1 by delta and 1 by 3 you can take it out. So delta QY plus delta QY 8, right? So you will get at last is equal to delta square by 12, right? This is an important formula of the quantization noise power. So you can say the quantization noise power equal to delta square by 12. So NQ is equal to delta square by, this is quantization noise power. Then now our aim is to calculate the signal to quantization SQ NR. Then I have to calculate the signal power as well. So signal power as well. So here to calculate the signal power here I am representing with the help of S. S is nothing but signal power. Here I am assuming the signal is single tone signal, that is MT is equal to AM cos 2 pi FMT. So from this you will get the signal power S is equal to am square by 2r, am square by 2r, right? And am r you can say is equal to 1, so s is equal to am square by 2. Now as we know, delta is equal to b max minus b min divided by L is equal to 2 to the power n. So this is the dynamic range, and the dynamic range for this signal should be 2 times of am upon 2 to the power 2n, right? So this is delta. As we know, the nq in terms of delta, nq is equal to delta square by 12, and after putting the value of delta in this nq, so 1 by 12 delta square 4 am square upon 2 to the power 2n. So right, so this is 4 3 is 12, right? So nq is equal to 1 by 3 am square upon 2 to the power 2n for the singleton message signal, right? And signal power you can write am square by 2, right? So this is the signal power in terms of amplitude. This is the noise power in terms of amplitude as well. So to calculate the SQ&R, you need to take the ratio of signal power to the noise power, right? You have the signal power here, you have the noise power here. So this is am square by 2, and this one is am square by 3 into 2 to the power 2n. This one is cancelled out here, so you will get s by nq is equal to 3 by 2 into 2 to the power 2n, right? So this is the signal to quantization noise ratio. So you can clearly see here, if you increase the number of bits, you will get SQ&R high, right? So you can clearly see here, as I stated earlier, that to reduce the quantization error, you have to reduce the step size, for which you have to increase the number of bits. If you increase the number of bits, so number of level will increase, and number of level will increase, you will get high SQ&R. So that's our aim, to have or to improve the SQ&R. So this is the important conclusion, right? So next, as we know, the just I need to take some space. Okay. I need to. So in terms of log scale, this SQNR, if you take the log of this, you will get in decibel. In decibel, this is log base 10 3 by 2 2 to the power 2n. So after taking the log, you will get 1 point approximately 1.8 plus 6n dB. This is another important formula. SQNR in dB is equal to 1.8 plus 6n dB. So this is another important formula, right? So here you can clearly see here, at last you will get the conclusion that if you increase the number of bits, suppose if you increase the number of bits from 1 to 2, 2 to 3, then you will improve the SQNR by 6 dB, right? So this is the so in general statement we can say, if you increase the number of bits by 1, then SQNR increase by 6 dB. This is important statement. So at last I can conclude the noise in PCN system, where we have the signal to quantization noise ratio, and at last I conclude this PCN system by this statement: if you want to reduce the quantization noise errors, then you have to decrease the step size, and for decreasing the step size you have to increase the number of bits per samples, and or you can say you have to increase the number of labels, and after doing this process you will get the improved SQNR, signal to quantization noise ratio. That is the our aim. So this is the noise in PCM system. Thank you.